So I think this last segment of um, the Scientific Data Mini Symposium is going to get more into applications. So I think we're going to start off with Romeo here. He's going to talk about KSVD.jl and how he got a huge speed up. So.
Yeah, all right. Thank you everybody for coming. So I'm Romeo. I'm a PhD student at Stanford. And I'm going to talk today about my implementation of KSVD, KSVD.jl, and in particular, how I got 150,000 x speed up over the baseline implementation. I just want to spend 1 or 2 minutes talking about what is KSVD. So just really quick, KSVD is related to the SVD algorithm, singular value decomposition. So we're kind of the domain of linear algebra. And what we will be doing is kind of speeding up particular linear algebra operations, and particular sparse linear algebra. So what the KSVD algorithm does, you have a data matrix that is kind of has a column of data, and then you have a lot of columns. Each data sample is one column, and you want to find a new basis for this data. And you want to find a basis such that you can actually represent each of the data samples by only summing up a kind of a very small number of basis vectors. So typically what you do, for example, with SVD is you can find a new basis that's orthogonal somehow, but in the end for each sample you need to sum up actually over all the basis vectors. And we want something that only sums up over a very small number of basis vectors. So you can kind of see that there's the sparse component of this where you multiply the sparse assignment matrix with the dense matrix. And that's kind of a theme in the talk today. So why is this important? So why are we using this? So actually my research is on understanding how vision and language transformer models kind of work and doing a safety assessment of them. And so one thing you maybe want to do is you know that in an image transformer, for example, you have these very high dimensional embeddings. And there's this theory that says, oh, actually, every embedding, even though it's very high dimensional, is representing kind of a few discrete concepts that are in superposition to each other. So what you're trying to do is you try to disentangle the embeddings, and you try to say, oh, actually, this embedding is only made up of a few kind of components which we can understand as a human. And so if you can do this, you can kind of do interpretability of these large language models, for example. And so I'm not the only guy who's working on this. There's this company, Anthropic. I mean, some of you know it. They're kind of an OpenAI competitor. And last year, they were also publishing a paper that does something like this. And they say, we want to do this for a large data set, maybe 1 million samples or 1 billion samples. Actually, this is kind of a known problem. And there's this algorithm, KSVD, but it's too slow, so it doesn't scale to the sample sizes that we want to do. And so Anthropic said, oh, we're going to give up. We're going to do some kind of gradient descent-based algorithm, even though the theoretical properties are much worse. And so I said, okay, I think the problem is not that KSVD is too slow. I think your implementation is too slow. So let me go ahead and see if I can make a fast implementation. And so this is where KSVD comes in. So by doing a bunch of work, and I'll just briefly touch on it, we were able to get about 150,000 times speed up. So here's a graph where you can kind of see I started off with this baseline implementation. And this was actually already Julia code. So this is written by this Japanese guy 7 years ago. And it was basically the paper taking all the equations from the paper, writing it in Julia and running it. And Julia is reasonably fast. And I looked at the algorithm and I say, okay, we need to get this like much faster. And I think we can actually get this parallel if we do a few algorithmic modifications, kind of change the algorithm just a little bit, and then work a lot on improving the kind of computation. And so by kind of repeatedly doing improvement, and measuring a lot which improvement actually help, you can kind of see this performance curve to kind of the speed up that we get over here. So before I talk about how we get the speed up, just really quick, if you want to use the package, you can just install it through the Julia package manager. It's registered. And so you can get your data embeddings from wherever you have them. And you can just run KSVD, and that's it. We're putting a bunch of effort into making it nice to use. And then there's also some more options if you want to get into more detail. And we'll, for example, talk about a little bit the executors that are kind of inside of this method and how you can dispatch on different execution strategies, different parallelization strategies. We'll get to this in a second. So now I want to take just a little bit of time about talking about the main algorithmic techniques or the modification techniques that we did to optimize this code. So actually, a lot of the speed up comes actually from algorithmic modifications. And so what you want to be thinking about is how can we kind of rewrite the algorithm to make it maybe reduce the number of required computations and also make it more feasible for threading it onto many tasks, reducing communication, trying to reduce the memory movement and so on. And so there's this kind of mixture of doing logical changes to the code and trying to look at the equations and rewrite the equation somehow. And one thing that's kind of very important there is that sometimes, or most of the time, you can kind of come up with different ways to compute something, but you don't really know what's going to be faster on one core, what's going to be faster on many cores, what's going to be faster on a distributed system. And so one thing I want to be pointing out is that benchmarking really is super important, and I'm going to show a little bit how we do this later. And also another thing, which is what we did, which is quite nice, I think, is you can have these kind of Julia types that you put in as a strategy at the top. So actually you say, okay, this time I want to run KSVD, and the sparse coding method, I want to use kind of this type, this execution type. And then later, when you implement your sparse coding, you can dispatch on the different strategies that you have. And so you can kind of do different things, and then you can measure if something is faster or slower, something is faster on many threads, and so on. And that's very important, and gets you kind of a lot of overview over if you're actually improving your code or not. So these algorithmic modifications get us about 600x speed up, which is pretty good, and then we get another 250x through kind of more code-centered changes. So there's a lot of reducing the number of kernel calls mostly being buffer allocations or memory allocations, so you can get like a lot of speed up there if you measure and you see, okay, actually we have a lot of overhead there. Of course, you want to make sure everything is threading nicely, and also this topic of buffer allocation and threading is a little bit complicated. And there's this package, Oh My Threads, that has a great kind of section on how you can deal with pre-allocating buffers in a multi-threaded setting, because Julia as a task migration is a bit complicated. And then we want to optimize cache hits. If everything else is really, really fast, you want to kind of see we have a memory-bound application, and so we want to optimize the cache hits. And so this is really how you get the last drops of performance. And for this, I want to talk about one other package actually, which is threaded and sparse mobile. And I don't have so much time to talk about this today, but I have a poster, and so you should come check out my poster if you want to see this. So we found we want to kind of do this type of multiplication, dense matrix times sparse matrix, and we want to do this multi-threaded. But everybody else only does sparse times dense, so kind of the opposite thing. And actually, there's no threaded implementation for this, even Intel, I didn't see one. And so we implement this, and this turns out to be actually much more cache efficient than this way. And so we're able to outperform MKL sparse, even in kind of their own domain, by about 2x, using very few lines of code. So there's this package polyester.jl by Chris Elrod, and it's like amazing. And you should check out my poster, I'll tell you more about it. All right. So let me just show you one slide. If you're getting started with like optimizing your own application, I can definitely recommend starting with profile view to get kind of an overview of your application. This is not my picture, but something like that. But what we've also done is to use timer outputs, and you can kind of go in and you can actually add a timer to kind of every method that you're using, and then you can enable the debug timings like this, and you can get a super nice overview over where your code actually spends its time. And now we can again go in and you can kind of dispatch on these different methods, and you can see for your application, for your executor, how fast it actually thinks, what actually does take the percentage of total time. And so if you do end up using this and you really want to squeeze performance, I recommend that you put in a few different of the executors, different of the parameters, for example, the chunk size and so on. And you can kind of measure very easily how you're doing. All right. So short time, short talk. I just want to say thank you to a few people who kind of wrote packages that really helped me. So the profiling package is super nice. All My Threads, which is a pretty recent development, but they have also some great tutorials on how to do multi-threaded kind of buffer relocation. Of course, polyester gets me the speed up in the dense sparse setting. K-SVD, a very nice SVD implementation from like 7 years ago. Yeah, and then I think you should all come at 7 p.m. To check out my poster on threaded dense sparse mole. And yeah, that's my talk today. Thank you.
Thank you. Any questions?
So I'm not so familiar with SVD, but what is your opinion on the SVD that's just in linear algebra. We use that all the time, but I see you also mentioning TSVD here and your KSVD. Like, how does it relate to each other? Is it like for completely different problems, or is it like a faster implementation for certain problems?
So the problem you're trying to solve is a little bit different, but it's related. So actually, the KSVD algorithm uses SVD inside of it, but you only use the first like main principal component, kind of the first singular vector. And so actually, one of the speedups from here to here, you can see this whole brown bar goes away. Why is it? Because we replace SVD with a kind of a something like a power method that only computes the first component, and this is actually TSVD, which does it for us. And so you end up using this kind of SVD or whatever many times at each step of the algorithm. Then you use maybe, let's say, 1,000,000 times or something like this. So this is the relation of the typical SVD and kind of the KSVD. And the reason for this is because actually kind of SVDs, you can think of it as kind of a convex problem where you at each step can kind of minimize a little bit better. But the KSVD has like a very discrete nature. So there's these sparse assignments, and it's not so easy to kind of just take a step, whether it's some kind of Newton method or whatever, to compute your minimum. So you have this kind of very non-convex character to it. And this is why you have to loop many times around SVD. And also why I think, and have also shown, that the Anthropic's sparse autoencoder gets actually worse results because it's gradient based and it can't really do the global search of minimum as well as this can.
Okay. Thanks. Yeah.
Thanks. Yeah, thanks for the talk. Very interesting. You use polyester. Is lock, is that an issue? Locking objects?
So
since you use threading?
Yeah, so that's a good question. So the question was locking, like writing to memory, for example, preallocated buffers. So that is something that we have. So what we ended up doing is we do these kind of mini batch approaches where you always say, okay, you focus only on the first, let's say, 20 columns, and you do each thread onto one column. You write into a copy buffer, which doesn't need to synchronize, and then you synchronize. You kind of spread the result again between all your threads. And if it's on one kind of node, this is pretty fast, but you kind of separate away writing to the copy buffer and then syncing. And now if you want to go distributed, you have to kind of do this again. But now we're all the time memory bound, so now you maybe want to have one hierarchy level higher. You do maybe 10 of these updates on different nodes, and then you sync. And this is something I'm also working on right now, but I'm also a bit like, it's fast enough for my application, so it's fine. But yeah, this writing to buffers, and especially in distributed, it gets quite interesting, and there's some trickiness there for sure.
Okay, if Christoph is in the audience, could you get set up? And meanwhile, are there any further questions for you, Christoph? Okay, well, thank you. Let's thank Romeo again, and make sure to go find his poster.